Hello, and thank you for your interest in BiasCorrector. With this openly accessible software, one can detect experimental biases in DNA methylation data. If necessary, these data can be appropriately corrected then to obtain accurate percentages of DNA methylation. In this video tutorial, we're going to consider one example and see how we can do the analysis. We'll discuss the format of input data, perform data analysis live, and correct biased data. The data may be generated by any quantification method, but has to be in a special format that is required by BiasCorrector. Two CSV files are required, one containing experimental data and another one with calibration data. A file with experimental data contains the quantified methylation percentages of the interrogated biological samples. A file with calibration data summarizes the quantified methylation percentages in calibrated DNA samples of known methylation degrees, for example, 0% methylation, 25% methylation, 50% methylation, and so on. As an example of an interrogated locus, we'll consider the methylation pattern of E-cadherin, which often undergoes aberrant hypermethylation in different tumor entities. Here is a CSV file with calibration data for 9 CpG sites of the locus obtained by bisulfite pyrosequencing. In this example, 9 calibrated DNA samples with known methylation percentages were included. However, the number of DNA calibrators may be reduced down to 4 if necessary. The number of technical replicas is not limited, as well as the number of interrogated CpG sites. This is a home page of BiasCorrector. We first confirm the use for research purposes and type in the locus ID. In our example, this is a E-cadherin gene. Next, we upload experimental data. So we select the CSV file with experimental data. Once it's uploaded, we can upload the next file, which is the calibration data. That's now successfully uploaded. Now data analysis can be started by pressing Run Analysis button. At this step, experimental biases are detected. To this end, regression analysis is carried out for each individual CpG site of the interrogated locus by using both hyperbolic and cubic polynomial regressions. Once the analysis is accomplished, a new tab is shown at the left, which is Regression Results. It contains 5 further subsections which we are going to walk through now. In Regression Plots tab, we can visually inspect experimental biases. In the graphs, the quantified degree of methylation, which is x-axis, is plotted by BiasCorrector as a function of the actual methylation percentage, which is the x-axis. That is done for every CpG site as well as the average methylation degree across all the interrogated sites. CpG sites can be selected from the drop-down menu at the right and can be navigated. Now, the CpG site number 1 is selected. Its ID also appears above the graph, as well as the locus ID. In the graph, we see 9 calibration data points and 2 regression curves. A turquoise dashed line depicts theoretical unbiased quantification, which follows the equation y is equal to x. The red solid line is the cubic polynomial best fit curve, and the blue solid curve is the hyperbolic regression curve. The more these curves decline from the dashed line, the higher the degree of experimental bias is. As already mentioned, one can navigate through different CpG sites in order to inspect respective regression plots. The publication-ready graphs can be downloaded at 600 dpi resolution by pressing Download Plot button. In the next Regression Statistics tab, we see a more precise description of experimental biases. Different parameters are shown here for the hyperbolic regression curve. This is this part at the left. And for the cubic polynomial regression curve at the right. The most informative parameters for us are average relative error. It shows the deviation of experimentally quantified methylation percentages from the actual methylation percentages. Sum of squared errors, or the value of SSE, it reflects the goodness of fit, and coefficients B1 and S. These later parameters, B1 and S, describe the degree of experimental biases. The parameter B1 approximates 1 in case of no amplification bias or PCR bias. And so, the more B1 declines from 1, the higher the degree of amplification bias is. Parameter S, which is summarized bias or total bias, comprises, in addition to PCR bias, other experimental deviations. It approximates 0 in case of no bias. In our example of E-cadherin gene, experimental biases are rather moderate, that is reflected, for example, in the values of B1 of approximately 0.5 to 0.6. We can additionally see that some lines are highlighted in green. The software automatically suggests a regression method for each CpG site. For example, CpG sites number 2, 6, 9, and average of all the CpG sites are going to be corrected by using hyperbolic regression method. At the next step, the methylation levels for other CpGs will be corrected by using cubic polynomial regression. By default, the software selects this regression method based on the minimum of the SSE value, which are highlighted in bold here. However, one can change that manually, as we'll see later. In the next step, corrected regression plots, we can visually assess the results of bias correction if calibration data are nominally used for correction. Here we see two graphs that are based on hyperbolic regression, that is left, or cubic polynomial regression at the right. Below, the diagrams illustrate the reduction of the average relative error after correction with either hyperbolic at the left or cubic polynomial regression method at the right. In our example of E-cadherin, the relative error is reduced from almost 23% down to approximately 3%, and that shows that the resulting corrected data are virtually free of experimental biases. In Corrected Regression Statistics tab, the regression parameters are similarly summarized, but now for corrected calibration data. Please note that the coefficients B1 and S are much improved as compared with the initial methylation data. For example, B1 is now close to 1 for the majority of CpGs. That means the PCR bias is eliminated, and the values of S are now close to 0. And the final step, before the actual correction of DNA methylation values in biological samples is done, is Select Regression Model tab. This is an overview of which regression method, hyperbolic or cubic polynomial, are going to be used for correcting methylation results for every CpG site of an interrogated locus. By default, the automatically selected regression types are applied as shown now, but we can manually change that like this, and we'll see this later in more details. Now we are ready to start bias correction. For that, press the button Bias Correct Experimental Data. A message may pop up about substituted values. The software notifies that some methylation percentages after correction were a little less than 0% or a little higher than 100%, and hence they got substituted by 0 and 100% respectively. Now, corrected methylation values are available. They can be downloaded along with all the plots and regression statistics as a compressed zip file. If you like, you may wish to reproduce this analysis by yourself by using example data on the home page of BiasCorrector and pressing Load Example Data. And finally, let's have a quick look at the Settings tab. Several parameters can be manually changed here. For example, the criterion for the choice of a regression method and parameters of plots. As we've already seen, the software automatically suggests the optimal regression type for correcting methylation percentages for individual CpG sites. In other words, either hyperbolic or cubic polynomial regression is selected. The criteria for that could be the minimum sum of squared errors, and this is a default setting, which is chosen now, or we can manually change that to minimize the average relative error after correcting the calibration data. Additionally, we can arbitrarily change the height and the width of the plots as well as the font size, so as to optimally adjust the plots for the needs of a user. These adjustments should be done, however, before running the analysis. For more information, please refer to our paper by Kapsner et al. And here are additional links that are also reproduced in description to this video. Thank you very much for using BiasCorrector, and good luck with obtaining accurate DNA methylation data.